Hi, welcome to my video about polymers. My name is George Smith, and the first item on the agenda, what is a polymer anyway? Polymers are molecules made up of loads of monomers. Mono means one or single, and mer means unit, thus a monomer is a single unit, whereas poly means many, thus polymers have many units in them, those units being monomers. Here there is an example with ethene being the single unit, and polyethene being made up of loads of that unit. Polymers are in basically everything, and by basically everything, I mean basically everything that is plastic. You think of something plastic? It's going to be a polymer. I'm going to show you some examples of things that are polymers by throwing them into view delicately. You can find polymers in this, one of these, this, that, this, probably that, and also in one of these. This is a model, and this is what my video today is going to be focusing on. First question, what is a model? Models are small plastic objects or figures made up of loads of little bits stuck together with glue. These bits usually come in some sort of matrix-looking thing called a kit. Here's one of them now. Models can range from boats, cars, trains, robot skeletons, and whatever the hell this thing is. So, I'm going to try and answer 3 questions in this video. What models are made of, how they're stuck together, and why they're made. I'm going to try and answer 2 questions in this video. Firstly, we have cellulose acetate. This is made from cellulose, a natural polymer found in wood. This is converted into cellulose acetate via reaction with acetic anhydride called esterification, with acetic acid as a solvent and sulfuric acid as a catalyst. In this process, the OH group in cellulose attacks the delta positive carbon and adds to the molecule. This breaks the double bond. The double bond, however, reforms itself and breaks the CO single bond. This negative oxygen then attacks the hydrogen and steals it. This results in the acetate group being added to the cellulose and a new molecule of acetic acid being made. This happens 2 more times to form cellulose triacetate. This is not what we need. To obtain cellulose single acetate, we use water in a partial hydrolysis mechanism to remove 2 acetate groups. Cellulose acetate was chosen for many reasons, the first being that it was tough due to the strong intermolecular bonds it had. Because the cellulose acetate had multiple OH groups, it had strong hydrogen bonds, which took more energy to break. It was also a thermoplastic material, which meant that it could be heated, melted, and cooled to a solid over and over again. This is quite useful when you need to melt something, put it into a mould, freeze it, and take it out, because if you make a mistake, you can do it again. It was also renewable because it relied on water and wood, and those are pretty much everywhere. But cellulose acetate was still replaced with this. Polystyrene, a polymer derived from the monomer styrene, which comes from petroleum, basically oil, natural gas, stuff like that. This was cheaper, firstly because it had a lower melting point than the cellulose acetate, and I'll explain that now. Polymers have 2 transition points, the glass transition point and the melting point. The glass transition point is when a glassy or rigid solid turns into a flexible, rubbery solid, and the melting point is when the rubbery solid becomes a liquid. An example of a glassy polymer is this bottle. An example of a rubbery solid is something like a rubber. For the glass transition point, a part of the chain has a localized cooperative movement, but for the melting point, the entire chain moves instead. Polystyrene has a rigid large side chain, which restricts the chain movement, and thus gives it a higher melting point because you need more energy to make it move. Cellulose acetate's flexible chains decrease packing, but its intermolecular forces are very strong, and thus increase its melting point higher than polystyrene's, making it more expensive to heat and melt. Anyhow, to make polystyrene, first you have to heat a peroxide to make 2 radicals for radical polymerization. The radical reacts with the double bond, breaking it and causing a new radical to form. The chain grows when this radical attacks another styrene, and this goes on, building up the polystyrene chain. The polystyrene chain only ends when either two radicals come together, or one radical takes the hydrogen off of another radical, ending up with one alkane and one alkene. Polystyrene is used because it's cheap, it's thermoplastic, and it's more inert than cellulose acetate due to the lack of reactive groups. Polystyrene is brittle though, as evidenced by this guy, this poor casualty of war. Usually, I would fix something with this, with glue, which I'll talk about now. Epoxy resins are a group of polymers with epoxides in them. They are thermosetting, which means that when they melt and solidify, they will only solidify once and will never melt again. These are the two most common compounds used to make epoxy resins, and this is their mechanism. Firstly, sodium hydroxide is added to remove the hydrogens from the OH groups. The negative oxygens then attack the delta positive carbons and substitute themselves in place of the chlorine atoms. If the ratio of reactants is correct, we'll have a half-reacted bisphenol A left over. This will attack the epoxide group and add onto it, producing a chain, a very long chain at that. To stabilise the negative oxygen, we add water so it attacks and steals the hydrogen, leaving us with a hydroxy group and a hydroxide ion. Curing is the process by which the epoxy resin hardens. This is done by adding a diamine and adding heat. The diamine's lone pair attacks the epoxide group and then is stabilised by the O- taking a hydrogen from it. But the diamine still has hydrogens it can give and lone pairs to donate, thus it can react more and create loads of branching between the polymers. The diamine acts as a cross-linker, connecting 4 different polymer chains, thus making a very tough polymer. Epoxy resin is used as an adhesive because it's extremely tough due to the massive amount of cross-linking, as well as all the hydrogen bonding it has due to the OH groups. But there is a different glue used a lot in modelling too. This is polycyanoacrylate, also known more commonly as superglue, made from the cyanoacrylate monomer. This is formed by anionic polymerization. Firstly, the nucleophile donates its electron pair into a double bond, breaking it and forming a carbanion. This carbanion then adds on to another double bond, breaking it and forming another carbanion, and this continues on to form the chain. Anionic polymerization continues until it encounters a proton or an impurity, such as here the chain stops when a proton is added to it. Cyanoacrylate is usually initiated by hydroxide ions in moisture, which is why superglue works on basically anything. Although nucleophiles don't usually add the double bonds, it does in this case because of the strong resonance stabilization of the carbanion. So, why do we use it? Well, it's extremely easy to use since it's initiated by moisture, and moisture is basically on everything. It doesn't need heat like epoxy resin, and it's extremely fast setting, which makes it extremely useful for building models. With materials and adhesives gone over, that's the end of my video. Go outside with greater knowledge about polymers in modelling. Goodbye.